Okay, let's start number 8 again. This is day 38, very last little part of it. We're doing 8 and 9 right now. So basically, if the company wants to guarantee that no more than 5% of the bags have fewer than 540 M&Ms, what mean should we try to achieve, assuming we keep the standard deviation at 12? So in other words, we're basically going to move this mean, and we would like 540. Okay, basically 540 is right here now. Okay, we want to move it so that only 5%. So we basically want 540, we want 5% to be below it. Okay, 5% to be below it, 95% above it. We can use the inverse norm here and get the z-score for this. So if we just want to know the z-score, so we want to know the z-score for 5%. Okay, and we're just a z-score. We're not going to use the mean and standard deviation here of 540. So inverse norm, because we're actually changing the mean, not our mean. Our mean was 550, so we are changing our mean, so that no longer applies here. All we have is our standard deviation. So we need to just do this in terms of z-scores. So we can just do this inverse norm. Okay, the area to the left is 0.05, and then leave our mean at 0 and our standard deviation at 1. And that will just give us a z-score. If we leave our mean and standard deviation at 0 and 1, then we will just get a z-score. So inverse norm, 0.05, I'm going to leave the mean at 0 and the standard deviation at 1 because we're changing the mean and standard deviation, so we can't use the 550 and 12 anymore. So the z-score is negative 1.64. Okay, so I need to find out what the mean should be. So I know the z-score, I know the standard deviation is 12, I know the x value is 540, that's the one I want to be 5%. So I set up my z-score formula, z equals x minus mu divided by sigma. There's my z-score formula. My z-score is negative 1.64. My x value is 540. I am looking for what should the new mean be, and my standard deviation I'm keeping at 12. So to solve this, I'm going to multiply both sides by 12. So negative 1.64 times 12 gives me negative 19.74 equals 540 minus m. So the way to get m is negative, so I need to move it to the other side. I need to add m. So then I'll get m minus 19.74 equals 540. And then I can add 19.74, so mu is 540 plus 19.74, just solving equations here. So the new mean should be 559.74. If I make that the mean, if I go for that average number, then I can guarantee, I could make a claim that no more than 5% of bags will have fewer than 540 M&Ms. All right, so if the mean must stay at 550, but they still have no more than 5% of bags have fewer than 540 M&Ms, what standard deviation should they try to achieve? So same scenario basically. We're still going to use our same z-score, but this time we're saying, okay, now we're going to keep the mean of 550. Okay, we're going to keep that mean of 550, and what should our standard deviation be if we want our x value of 540 to be 5% at the 5% mark, which, as you recall, the z-score for that was from the previous, right up here, negative 1.64. So we're basically going to set up the same equation we just did. The only difference is, instead of the mean being the unknown, the sigma is. We're going to keep the mean and make the sigma the unknown. So I'm going to set up negative 1.64 equals 540 minus 550 all over sigma. So what should sigma be if I want this same characteristic as up here? So I need to multiply both sides by sigma first. So negative 1.64 sigma equals 540 minus 550 is negative 10. And then all I have to do is divide both sides by negative that's a sigma, negative 1.64. And that'll give me that sigma should be, well, negative 10 divided by negative 1.64 gives me 6.10. So if I make that the sigma 6.10, the standard deviation about half the size of what it currently is, then I can make that claim too. So you've got your homework here, homework number 33, some more odd problems to try. Basically we've done the same thing for 3 lessons now, only this time we had our calculator to help us using the normal CDF and the normal PDF. So I'm going to move on to the next day of notes, and this is day 39. So day 39, this is a really short little day. It's actually going to be combined, well, there's a second part of day 39, so I'll make another video for that. So that is starting chapter 16. So this is the very end of chapter 6. So in many problems, we assume that a distribution is normal. In real life, however, a set of data will never be exactly normal. Still, the normal model can be a useful approximation if data are close to normally distributed. To check if data is normally distributed, and this is what you have to do every time, we could look at a dot plot, a histogram, or a stem plot, since these both show symmetry, skewness, and modes. Basically, if you look at any of these, dot plot, a histogram, or a stem plot, what you're looking for is unimodal and symmetric. Okay, and then you can say we can definitely approximate with the normal distribution. Okay, but the best way is coming up. How do we actually show for sure that distribution is approximately normal? So, however, even dot plots, histograms, and stem plots are not as useful as a normal probability plot. Normal probability plot, called the NPP. Normal quantile plot is what it's referred to sometimes. They've got pictures of it in your book if you read chapter 6. So, in a normal probability plot, the actual data are plotted on one axis, and each value's theoretical z-score is plotted on the other axis. So you're looking at the data and the z-score. So this little graph down here, here's the data, and here is the z-score that goes with it. So the z-score is a number between, negative whatever and whatever, 0 being the middle. The number of standard deviations you are above and below the mean. So, for example, in a data set with 100 values from a normal distribution, the smallest value should have a z-score of negative 2.58, and the highest should have a z-score of positive 2.58. To estimate this value, imagine taking many samples of 100 from a normal distribution, sorting them, and finding the average z-score for the minimum value of the samples. The average z-score of these minimums should be about 2.58. So if a data set closely follows a normal distribution, here's the key, here's how you read it. If you have a normal probability plot, here's how you tell if the normal probability plot is good for a normal distribution. Is your data good for a normal distribution? That's what this is looking for, telling you right here. So if a data set closely follows a normal distribution, then the normal probability plot should look linear. Right there, there's the key. However, if the normal probability plot is not linear, this gives evidence that a normal model may not be appropriate. If it's a normal model, basically you should have values all along from the lowest to the highest z-score, and it will make just a nice little straight slanty line. Okay, so if your data, here's your data, if it's approximately normally distributed, symmetric and unimodal and symmetric, then the normal probability plot will approximately line up on a straight line. And this does, there's a few of them that get a little far away from it, but this one does. So this would be just fine. Yes, a normal model is appropriate since the NPP is linear. That's what you say every time. You show a picture of the NPP, you say yes, it's appropriate because the NPP is linear. So how do you graph that? Well, in your stat plot menu, so second stat plot, you're going to turn your stat plots on, and if you have the data to put in, okay, your normal probability plot is this last one right here. That is the normal probability plot. It says the sixth graph choice is the normal probability plot. So we haven't really had any where we've got a whole bunch of data, but we will in chapter 16. So this is how you actually decide if a normal model is appropriate, assessing normality. You look at the normal probability plot. If it makes approximately a straight line, then a normal model is appropriate. So homework number 34, and you'll also have 35 on day 39 too. I'll do that in the next video.